Earlier we had a question about the difference between interfaces and something called type aliases. And these are both ways of giving a structure a name that we can import and export from modules and we can refer to. The main benefit is we have one central place where a type is defined and it can be used throughout a code base. So we're going to study these two concepts and compare and contrast them. Along the way, we're going to touch on different types of signatures, which includes the kind of signature we're used to for invoking a function, and something called an index signature. We will discuss the idea of open interfaces, and this is a way that you can augment types that you may import from a library somewhere. We will discuss the concept of access modifier keywords, which gives us control over who can see methods and instance data when it comes to classes. And finally, we'll touch on heritage clauses, which is just a fancy name for extends, right? You're used to extends from JavaScript classes. There's a new one called implements that comes with TypeScript. So we'll open our notes to the page that starts with 3, interface and type basics. Type aliases are they're a really simple concept. It is literally giving a type a name. Any type that you can use with a variable, you can also create a type alias for. So when I say like string or number here, what I mean here is anything that could exist in this space, you can create a type alias for. This is not true for interfaces. So type alias is actually more flexible than an interface in some way. This is the only time you'll ever see a type appear on the right-hand side of an equals. Well, there's one other, but it is really the identical concept, just in a slightly different syntax. But we're exclusively working in type space here. This will compile to no JavaScript at all. One of the challenges with type aliases is that they're defined and figured out by the compiler in terms of what values are allowed inline as the file is parsed. And this prevents you from creating self-referential types. So let's say we had a data structure that we wanted to create a type for that looked like this. 1, 2, 3, 1, 1. Right? It consists of 1s, 2s, and 3s, but also a nested array. Really simplified kind of JSON-ish thing. Like there's some hierarchy here and a set of allowed values. We could try to type this saying that the value can be 1, 2, or 3, or an array, where an array is an array of num-vals. But TypeScript compiler is not happy. And the reason is it wants to conclusively figure out what num-val is all about before it moves on to the next line. And it has not yet encountered this. So it runs into a circular problem. It's like a chicken and the egg problem. To define A, we need B, which needs A, and so follow that all the way down. So we will loop back to this and explain how this can be. We can use this to our advantage. We can use this weakness as a strength. So we've already looked at interfaces. I want to point out that interfaces can extend from other interfaces, like same syntax that you're used to seeing with classes. Just remember that extends is used for inheritance of like things. Interfaces extend from interfaces. Classes extend from classes. So here we're just adding country code to something that already has a phone number and a name. We can use an interface to describe a call signature. And we're simply using parentheses here. So this describes a function. Now, what we're starting to see is interfaces can describe objects. Interfaces can describe functions. In a moment, we'll see that interfaces can describe arrays. So we're dealing exclusively with JavaScript values that extend from the JavaScript object type. We've not yet seen, and we won't see, an interface being able to handle primitive types or operators used with types like string or number. There's no way to describe that with an interface. So that's one clear difference we're seeing here. Type aliases are extremely flexible. They can handle the primitive stuff. They can handle most things that an interface can handle, everything that an interface can handle. But interfaces are limited to JavaScript object and subtypes, which includes arrays and functions. Things that have prototypes. Think of it that way. So here's a function signature, and here's the equivalent with the type, right? The wrapping's a little unfortunate here, but same idea. This is one signature, and the only difference I want to really point out, because it's a little subtle, the return is void here, :void, and just to make parsing possible, we use a fat arrow here to define a function type with the type alias. This would not be valid. One cool thing about function types, Prettier has hosed me a little here. One cool thing about function types is we get something called contextual inference. So we've already defined this type, contact messenger 1. That's right up here, right? Turns out, we don't need any additional work, no additional type information in order to figure out what the return type should be. What should these arguments type be? Or what should the argument types be? That's all coming along for free because that information exists here. You'll see the same benefit come through with callbacks, right? If you say, I accept a callback and its value, like the signature should be this, now at every invocation site, every time you pass a callback along, you can forget the type information. The type checking still happens exactly as it would, but you don't need to be so explicit along the way. Construct signatures look very similar to call signatures. All you need is new ahead of that. You're used to seeing this in a class, right? Classes are something, they're newable. We can use the new keyword with them. So this would be a way of describing a constructor that instantiates either things that have an email address or a phone number and definitely have a name. Here's our array example. Index signatures, which look like this here, square brackets make sense, right? Because that's how we access a property off of an object with an arbitrary key. We're saying if you access a property off of phone number dict and give it a string, it'll either not be there at all or it'll have this form. Now, when you're defining a dictionary type like this, and a dictionary is just a key value data structure, you have almost certainly used an object as a dictionary before in JavaScript. Property keys with consistent object types, right? You've got to be careful that you don't type this in such a way that TypeScript gives you a false guarantee that no matter what property key you pass in, you will definitely get a well-defined value out. Let's look at what would happen if we did that. So an empty object is a valid case here, right? No keys. And no matter what I do, it's acting like there's something there for me. This is a hard to track down error waiting to happen. So don't do that. By adding undefined, we force a check on this. And what you'd have to do is something like this. See how up here the undefined is present? And inside the block following the condition, the undefined has disappeared. What we have done here is narrowed the type. TypeScript understands that this condition, that it understands that this type here can never have a truthy value, never. So there is no way for an undefined value to pass into this block here. And this is the proper use that we would want anyway, because if we're just handed something and we're told that it's this type, we don't necessarily know what's on there. We don't know which keys are valid for looking things up. So conditions can be used to narrow types. We could do it a different way. It's just the inverse, right? We're checking to see if the type of d.abc is an object. Let's see what happens with this. Oh, impossible. This is like, in terms of the Venn diagram, TypeScript's always trying to figure out a way to make things work. This is a situation where it's saying like, okay, this can either be undefined or an object. So now we have some code that would run in the case where it's a string. Never going to happen. Never. So you get a never. I'll leave that there just so you can follow up on that. Okay. Here's our phone number dictionary, and this is just demonstrating that we can place values in there. If we misspelled something, we'd get busted on it, right? It's telling us there's no ARA code. We have to spell that right, area code. I'm going to try editing it in a second, but let's just see what happens right now. So we can eliminate it because if this were in our like contacts page in our phone, we could have multiple phone numbers there. Some people are not going to have a home number. They'll only have an office number, so this is fine. So it looks like the structure of these values here, that's enforced, but we have total control over what the property keys are. One thing that's important to know is that you can only have, at most, one string index signature and one number index signature. So you could change this to like number and have something slightly different than if you passed a string in and tried to access a property that way. So we can use index signatures in combination with other types. And this is where I'm actually showing off a couple things here. Number one, I have created another interface with the same name of what we were just using, right? Up here we had phone number dict, and now down here, same exact name. And if we look at this, if I try to remove it, we're now getting an error. So let's look below and study what we've added in order to figure out why something might be erroring. What I've added is new types that kind of say, we have new required properties. Everyone must have a home phone number and an office phone number. And the index signature still exists underneath all of that. So that's what's making it so if we attempt to delete this up here, we're getting an issue where home is missing. Now we could totally add another one here safely. iPhone, I just need a comma. And that's fine. And we're free to add and remove this as we see fit. So you can use index signatures in combination with anything else that we have learned about object types. Often this will be a fallback where you specify certain things, like we know we can access these things. So for example, it would be convenient to be handed this thing. I don't have to check whether home and office are undefined. Like if you know they're present for sure, it's much nicer to be handed this thing that's like ready to go. But there may be optional extra stuff there, and an index signature would be a way to facilitate typing that. We kind of demonstrated this already, but home is definitely there. Office is definitely there. Mobile will have the undefined due to the index signature. So what we're seeing here is declaration merging, and we're seeing that we can stack indexes on top of other things. The last thing I want to point out about interfaces loops back to the type alias discussion we were having earlier. Interfaces are kind of like functions. They're parsed like functions in that we know that an interface exists and has a particular name as we go through and parse things. But only when we attempt to actually access it and use it will we end up figuring out what are the allowable types for this thing. So type aliases are kind of sorted out eagerly. Interfaces are sorted out lazily. So if we were to go up here to our first example, and we were to say, we were to try to figure out a way to make this type work. If we were just going to say interface, number array, and I'm going to cheat a little bit here, extends an array of numvals, now this semicolon, now this ends up working. Why? Because this is kind of like, just like a function, it's hoisted, so we can refer to it before it's used, or before it's defined. Numval, by the time we go through and sort this out, this is actually happy. It's an interface. Now, until we get down here and sort out all of this, we don't necessarily know what this interface can hold, but at least we can refer to it and use it as part of the definition for the type alias. So you can create things that are sort of hierarchical types, self-referential types. Some people call these recursive types. But you can create things like this through combining types and interfaces. Let's make sure I'm not lying. Looks good? Let's try this. Looks good. 4 makes it unhappy. So it can hold our nested arrays. It can hold the simple values we're interested in. Everything looks copacetic. So that's, hopefully now you understand the difference between these two. Type aliases are eager, interfaces are lazy. Type aliases are extremely flexible. They literally can give a name to any type. Anything you would use as the type of variable fits in a type alias. Interfaces are what you will want to use for things that are objects, which includes functions. It includes arrays. When I say things that are subtypes of object, I mean in the JavaScript sense. Things that are your mutable things, right? Everything except the primitive, like string, number, Boolean, symbol, undefined, null. I want to also show you this test here. So you can write tests for types. Microsoft has a library called dtslint, which uses tslint, and it basically parses the linting error messages and compares them against special comments that you can leave in your types. So this isn't actually, I kind of lied when I said it was a Mocha test. This is just a TypeScript file with special comments in there. And this basically asserts that if there's an error, like there must be an error here. I could just as easily say expect type false, right? You can write test cases around things that are purely types. A lot of people don't realize this, and they just skip tests completely when it comes to interfaces and things like that. But this can be a gnarly area of your code where, you know, if you have something that's a little bit abstract, you really want to have some confidence around changes being non-destructive.